Multi-robot flocking plays a critical role in real-world applications such as wildfire monitoring, search and rescue, and wildlife tracking.
In these missions, maintaining a stable and coordinated formation is essential for effective operation. Recent advances in LLM demonstrate its potential application in multi-robot control. However, previous studies show that directly applying LLMs to control robot teams often results in unstable or disorganized formations.
To address this limitation, we introduce a new framework called LLM-Flock that combines LLMs with an influence-based planned consensus strategy.
Our framework starts with a task prompt provided to each robot, specifying the desired formation or behavior.
Using its own LLM, each robot independently generates an initial plan.
The robots then share their plans with nearby neighbors and adjust their own plans based on the influence of those neighbors. This planned consensus process runs in parallel with motion execution. At each step, the LLM helps the robot decide its next move. As the robots continue to move and communicate, their plans are continuously refined, enabling the team to achieve a coherent and unified flocking formation. Robots determine influence based on the number of neighbors within the communication range.
If the neighbor robot has a larger influence and the plan between those two robots is different, the robot with less influence will adopt the plan from the more influenced robot. These influence weights are dynamically updated in the tests, enabling stable consensus. We present simulation results using our proposed LLM-Flock framework.
In these tests, we compare our method, which uses influence-based plan consensus, with a baseline that relies on basic planning. In the baseline, each robot plans and moves independently without any coordination. All simulations use OpenAI's O3 Mini as the LLM backend. The first experiment shows 3 robots forming an equilateral triangle. Each robot begins with its own plan, indicated by the color of its disk, which reflects the origin of the plan. As they move and communicate, the influence values above the robots increase, guiding them toward a shared plan. By the end, all disks show the same color, meaning the robots have reached consensus and formed the desired triangle. In contrast, the baseline fails to produce a stable or evenly spaced formation. Next, we increase the complexity with 6 robots trying to form a larger equilateral triangle. Our framework still leads the team to a consistent and correct formation. The robots gradually align their plans and move into place. Meanwhile, the baseline robots fail to stabilize.
In the third experiment, we test 8 robots forming a square. Again, the influence-based consensus helps all robots gradually reach a consensus. The final formation is evenly spaced and well-aligned.
On the other hand, the baseline robots remain poorly coordinated.
Finally, we test a circle formation with 10 robots. Our framework successfully produces a symmetric and smooth circular arrangement. Each robot contributes to the overall shape as it adjusts its position based on the plans of its neighbors. The baseline test fails again, with robots spread unevenly and not form the stable formation. We also validate our approach with real robots. In this experiment, we use Crazyflie 2.1 drones equipped with the Lighthouse positioning system for accurate indoor localization. Each drone runs the O3 Mini LLM as its decision-making backend. We first show 2 simple formations. In the first test, 3 drones form an equilateral triangle. In the second, 4 drones are arranged into a square. Next, we test more complex cases involving 5 drones.
In one scenario, the drones form a cross pattern.
In another, they arrange into a circle.
In summary, our integrated approach, combining parallel execution of LLM-based plan generation and robot motion together with the influence-based plan consensus, significantly enhances multi-robot flocking capabilities.
For comprehensive details, please refer to our full paper.